recording.
Okay, unser heutiger Vortrag hier im zweiten Slot des zweiten Blocks in Raum Eliza ist die Vorstellung des Projekts Hannah.
We'll present the Project Hannah,
offenen Plattform für
an open platform for walking robots. The project covers both hardware and software. I personally love robots and I'm looking forward to the talk. The people talking to you are Matthias Kubisch and Felix Just.
Ja, ich freue mich mit euch zusammen und lasst uns eine Runde Applaus spenden an unsere
Let us give a hand to both of our speakers.
Ja. Hallo, herzlich willkommen zu unserem Talk.
Welcome to our talk.
Kriegen wir Bild?
Will we get a picture here?
Ach du? Ja, darf man.
It's your problem. Much better.
Genau. So, jetzt ein bisschen an. Sie tippelt da vor sich hin.
So she's talking. She's walking.
Geht das? Ist zu groß? Geht so.
Ja. Aber jetzt nicht mehr. Hier.
Is it too big?
Ja.
Achso. Verzeihung, wir haben das klassischerweise nicht richtig vorher getestet. Wir haben es ein bisschen vorher getestet, aber...
We have tested it a little bit, but not fully.
Test-driven Talk. Das
So.
haben wir schon mal gesehen. Dann machen wir das doch so. Dann siehst du das quasi hier gleich da auf dem Bildschirm.
Das reicht mir auch, wenn du mal Bild.
Schau mal so.
Genau.
So.
Da tappelt sie vor sich hin,
She
versucht
walks.
über die Gehwegplatten zu kommen.
She walks over the
Laufen doch ein
tipping
wenig erschweren.
plates, which makes walking more difficult.
Schwupp. Du schaffst das nicht.
Ich schaff das. Man sieht, wenn man nichts sieht, ist das blöd.
Okay.
Da auf dem Bildschirm sieht man nur die Hälfte. Sehr gut.
On the below screen, you can only see half.
Genau, also nochmal von vorne. Willkommen zu unserem Talk.
Welcome to our talk.
Wir sind Matthias und Felix.
We're Matthias
und
and Felix,
über unser Projekt Hannah berichten.
and we'll be describing Project Hannah.
Wir sind aber nicht die Einzigen, die sich damit beschäftigen. Wir
We're
sind
not the
eigentlich
only
zu
ones.
fünft.
There's 5 of us.
Na gut.
Haben wir noch mal eine Chance irgendwie, dass wir das hinkriegen?
Genau. Ich kann trotzdem erzählen, die Namen kenne ich.
I know the names. I can talk to you.
Mario Lasek,
Mario Lasek, Frau Scheunemann,
Matthias
Tom
und ich eben
Lobig,
und haben in den letzten
Matthias and
2
I.
Jahren, jetzt.
Marike.
Haben in den letzten 2 Jahren zusammen Supreme Machines
And
gegründet.
over the last 2 years,
Den Roboter.
we have founded Supreme Machines.
Wir haben da das Logo von der Humboldt-Uni, weil Matthias da
We have taken
ist und auch der Paul dort beschäftigt ist.
The logo from the university,
DLR,
because he's a
Museum für Naturkunde, und das X-Hein-Logo, das
a
ist der
student at the-
Hackspace, den ich so nebenbei noch betreibe.
and
Und,
so Supreme Machines is my there's my Hackspace logo.
Stattgefunden haben.
So that's
Und,
where it all
was
comes
du
from.
so erzählt das mal Matthias.
And Matthias will give the introduction,
Also unser Talk ist
the
heute
overview.
einmal über die Roboter-Hardware.
Today
und
we'll be
über
talking
quasi
about
das
hardware
Designprinzip, was wir verfolgen.
and the design principle.
Und da in der Hardware steckt natürlich auch Elektronik.
Inside the hardware is some electronics,
Also das ist, wenn man so will,
some
kommt alles aus einem Haus.
mechanical components. Everything comes
Und,
from us,
Wir gehen ein bisschen auf die Firmware ein und später
and we'll
wir
talk
quasi,
some about the firmware
unsere neuronalen Netzen für die Regelung schrauben.
and how we are working on neural networks for the control.
Zur Introduction. Was ist unsere Mission? Unsere
Our mission is
wir
to
möchten gerne, dass viel mehr Leute, also im besten Fall auch nach dem Talk einige von euch, die hier sitzen,
enable more people
vierbeinigen Robotern Lust haben zu arbeiten,
to work with 4-legged robots, to build them, to try new ideas,
wundervolle Technologie noch weiter voranzubringen, die noch
and to
stark in den
bring
Kinderschuhen
wonderful
stecken.
technologies forward.
Lustige Videos im Internet,
that
aber
currently
wir
are
noch nicht durch unsere Straßen laufen. Da ist noch
visible in the internet, but we don't see them walking in the street. Some of us want this.
Und genau. Deswegen möchten wir quasi eine Plattform bereitstellen.
And this is why we wish to offer a platform with which many people can experiment, that is easy to assemble, is affordable in pricing,
daran Ideen entwickeln können.
and so that people can learn with it and can develop ideas and bring the state of the art forward. We've had a problem 2 years ago because we wanted to build robots, because we had ideas what can be done with them. We wanted a pizza oven that delivers to your home, that knows when the pizza is ready and delivered to your door just in time. But building robots is harder, so you need stronger motors. Those are expensive. Some things are fantastic, but they are difficult to find, and there's specialized component manufacturers.
Oder man kriegt halt irgendwo so eine schöne closed source black box.
Or we get a closed source black box, which we don't really like.
Roboter kaufen ist
And to buy a robot is not an alternative, because most of them are either toys, and they won't allow you to transport a pizza, or the ones that could do it, the more promising ones, they are infinitely expensive if you can buy them at all. So we thought about what's possible. Either you continue using toys,
oder man kauft die großen teuren Dinger.
Or if you can afford it, we build one. If you work at a large institution.
Oder man verbringt halt 2 Jahre damit.
Or, as we did, you spend 2 years constructing your own.
Das ist das, was wir gemacht haben.
This is what we've done.
Viele andere Wege gibt es da gerade nicht.
There aren't many other options.
Ja, so nach 2 Jahren haben wir.
So after 2 years, we are proud and show you today an open source robot with a modular, distributed open source control system. Many feedback information from all the sensors that we built. We have done it on the side without financial backing. And the material bill of material costs about 2,000 euros. Is much better than the others. We've taken components that are easy to find. We're proud of the construction. It's not a Lego set, but none of us is a car mechanic. We managed. So it's easy to build. So why open source? We don't really have to explain it much here in this audience.
Offene bzw. freie Hardware-Designs werden einfach in Forschung und Bildung gebraucht.
We need open and free hardware designs in research and development and education.
Weiterentwicklung zu machen, das
there are opportunities to develop it on further on your own. That affords the possibility of multiple different versions and varieties.
Und nachbauen. Und man kann halt irgendwie im Zweifelsfall auch mal überlegen,
so
was kann ich da drauf bauen.
You can get the maps, the construction plans from the internet, and
beschäftige mich mit das, was ich da drauf baue, und nehme einfach eine laufende Plattform.
And you can actually take it and assemble it and then start building on top of it. For us, it is important to contribute to finding the best design for four-legged. We don't think that ours is the ultimate solution for all problems. So if anybody has a good idea on how to improve on it, it's a big search. So we provide one sample and we expect many more from you.
Genau. Ja, also wir haben es ja irgendwie schon mehrfach erwähnt. Wir wollen.
We've mentioned it multiple times. We want an inexpensive, easily accessible, with easy replacement parts robot. And in all choice of components, we obeyed that principle. And that is why we've used standard components. Ball bearings, screws, all these things, they are available from multiple manufacturers, and and can easily be sourced. Things that are non-standard, we've 3D printed in our hackspace. They aren't high-end 3D printers. We've used a laser cutter to build the legs, and it can be assembled with the normal toolkit from a standard home toolkit. So it isn't pretty. There's a long way to make it pretty, but it works. We haven't thought about how will it be and constructed it and then built it. We've started with very simple tests from zero. So we've taken measures, stick measures, and taped them together. And then we've checked how we can get a joint on a leg. And in the end, it needs to be wired up and and you don't want the motors to be loose. It might look funny, but it's not the aim. So here you see the 5mm planar wood that we've laser cut. I strongly discourage trying to do this by hand. We have printed many pieces from a 3D printer for two reasons. So the knee joint, they are simply not available for purchase. We had to design them ourselves. And the wheels, we made a 3D model. Somebody might say you could buy them, but it's very hard. For a start, they would be made from metal and more heavy. And secondly, you would have to be able to obtain the right diameter and the right connector for the motor. So sourcing is very difficult for these parts. So we've designed it ourselves and we've printed on PLA or tough PLA. Den Zahnriemen an sich zu finden, als die Dinger stabil the hardest part was to find the belt. That was harder than to get the wheel stiff.
Zahnriemenrad spricht, ist halt, dass man möchte es ja an seinen Motor anbringen.
One of the problem is the problem of the wheel is that you have to connect it to the motor, and when you exchange the motor, you still want to connect it.
Der Tom von uns, der ist ja ein Fuchs, der hat das als parametrisches Modell gemacht.
So Tom made a parametric model so that we can change the ratios.
Wir können jetzt hier irgendwie, also es sind in der Tat 42 Zähne.
And we have one with 42 teeth.
Hier sieht man noch mal ein bisschen mehr dann vom
So here you can see some more of the composition.
Wir haben verschiedenste Farben verdruckt.
We printed multiple colors, and you can see on the right-hand side from your perspective the motors. And we made lids for the motors so that we can put our own circuit board on there, and that goes to the electronics.
Right. As you can already think, inside such a robot there's lots of electronics. Every motor needs to be controlled with a separate control unit, so there needs to be a possibility that each motor is communicating with others, and therefore we build a system which is two-stage. So it's a tree structure you see here. With L, there's these are the controllers, the limb controllers. They are built in 5 of these, and 4 of them controlling a leg. on which the motors are hanging, and the motors themselves are then connected via a bus system, which is shown in pink. And these are the possibilities to address each motor individually. So you can read out the sensor data separately and then control each motor according to that. On the graphics, there seems to be a mistake. It's white, not bright gray. They are hanging on their own bus system and then controlling their data. There's one computer which is handling all the data. In addition to that, there's the battery system, which is separately. So we are using different batteries for each controller. Therefore, you have the possibility to not use one heavy accu in the middle, one battery in the middle, but distribute the mass of the batteries over the body, like in the legs or in the body, which might be useful for the modification of this might be useful to make the robot walking more easy. And then there is a certain voltage regulation circuit made from diodes. Our motor regulation system in the legs, there are 12 of them. We call them sensory motors because they are using the sensory data, reading them out 100 times per second, sending them to the main computing unit. And we could now read out the data sheet, but you can read out current, voltage, and position of the motor individually. And this will give you the information how the joint is adjusted right now, how is the force from the motors to legs. Also can regulate read out the voltage and current, so you know which energy is used right now. You could also add several more sensors. At the motor 0, for example, there is an acceleration sensor. Beside that, on our controller, there is a slim circuit which can be adjusted. For instance, we could, so it could be anything, basically. You connect there. This is the limb controller. It has a bit more power. It has a floating point unit on it, so you can calculate neural nets on it. And later on, I explain they are calculated, distributed over the robota. So each limb controller is calculating the part of the neural net it is needing for itself to control the legs. So each one is connected to the other ones over the bus. The bus system itself is an old industry standard, maybe even too old, outdated. Just to tell for the electronic people here, if you want to solder it yourself, you have 2 wires which are carrying the signal, and the transceiver is subtracting the signals so that there is noise filtered out. You have an electrical filter which is given by the physics, and there is much more stuff. And you can see that each motor is in a kind of bus, so it gets in one time step the data. It gives the data to the bus with in a certain time step, and then it's depending on the protocol when and which motor is speaking to the bus. But this is not specified. It's just the physical layer. Thereby, it's pretty similar to the CAN bus from the automobile industry, but it's a bit more budget version of it. So it's basically has the same functions, possibilities functions. The firmware is pretty modern. in contrast to most other firmwares which are coming in C. We were using the XPCC framework. It's now called modem without the E, modem, because it is cool because you can switch from one platform to another just without taking care of the platform. You can switch from one chipset to the other without modifying your software. For instance, in one of our motor controllers, there is no Atmega but an STM, so we didn't need it to write a different firmware for this, but could use the same as before. All is running on a 100 Hertz basis, so this is pretty slow for normal robotics, but as the protocol is open source, if you have fun to work with the system and pimp it a bit, you can go to a kilohertz and tweak your own firmware so that it's a bit faster. So the possibility is there.
Ja, und jetzt kommt es an den Teil.
Und jetzt kommt es an den Teil. And then now we come to the part that I enjoy.
Mich mit Laufalgorithmen und Laufen lernen, selbstständiges Laufen lernen für Roboter beschäftigt und
so I've spent my time with learning walking for robots.
Irgendwie also weil ich halt in der Simulation hauptsächlich 4 Beine hatte, weil das
and in the simulation I had 4 legs because that's an elegant form and an elegant morphology, and I didn't have a robot.
Das einfach selber zu versuchen oder
so I tried it self, or I just tried
also da ist noch viel ausbaufähig
to do it myself.
Aber jetzt würde ich einfach mal gerne erzählen, was quasi
so ultimately it can be extended, but I'll describe where we are with the controller.
Es ist relativ üblich zu der Hardware auch einen Simulator zu bauen.
It is quite usual to build a simulator for the hardware, and in this case we did it the other way around. I already had the simulator, and now we build the hardware to the model, to the simulator. The blue curves are the motor controls, and the orange and the white have a very low amplitude, and they are position and location values. A student of ours, Daniel Hein, left me his robot simulator from his master's thesis, and he wouldn't recognize it, but I kept the name. And I'm very thankful to him because I could just build right on top of a simulator that I could tie to this research effort. The limits are its own, but this robot has 12 joints, has many sensors, many of those. So we use the angles and the angle velocities, and in the center of the body we get acceleration, and they all go into the controller. So now we have 12 joints, angles, angle velocity, the last time what we fed into the motor, and what do we do now? So on this model it's not obvious. For Mario Brothers it would be easy how to control it, but and it is very hard to think about it and tune the parameters. And I very quickly moved on to learning algorithms. So my effort was to teach the robot to learn rather than to build it myself. It may take longer to train it. But you may be able to program a walking faster.
Ich finde die richtig schön, aber ich will die jetzt auf der Hardware sehen. Ja? Nur in der Simulation reicht mir nicht. Und,
so I like the way it walks, but I want to see it in hardware. So here is how it works. Look away if you don't like math. You have a very large state vector.
Das Problem ist jetzt einfach für den Algorithmus sieht das Problem formell
For the algorithm, this is the formal problem for the algorithm. It takes an input vector, the angles and accelerations, and an output vector that we can describe, and we get a feedback. And it doesn't know any more than that. So I don't give it, the robot has 4 legs or whatever. So the algorithm only sees the input and what it can send out. And it tries something, and the algorithm somehow tells it some number. And then it has to change something to get it right. So if we think about on the left-hand side,
ganz links sind die Inputs, das sind quasi
that's right.
alle Inputs, die der
Here's the inputs,
plus das, was im letzten Zeitschritt
plus
an die Motoren geschrieben hat.
what we told the motor in the last time step, so that it doesn't forget, and then it can write it out to the motors.
Das ist quasi eine Gewichtsmatrix, die
and the B is a matrix of weights. It's a you can look at it as a single neural net.
Wenn ihr rechnen könnt, dann wisst ihr, dass 12 mal um die 40
So
große Zahl
there's a question how you find that matrix.
Ihr seid in einem Tonstudio, habt irgendwie dieses
So it looks like
große Mischpult
you're in a recording studio and you have a very large mixer, and you don't know what each knob does, and sometimes the band says this is horrible, and sometimes the band says this is great. And this is how the learning algorithm sees the world. It gets feedback on whether things went well or went badly. And we have to adjust many of those knobs.
Eine künstliche Evolution erledigen.
We allow this to be done by artificial evolution.
Und die funktioniert ähnlich der echten Evolution. Also es gibt
And it's similar to real evolution.
Regler werden ausgewürfelt und die werden dann
So
ausgewählt.
we randomly choose
Läuft dann, fällt auf die Nase. Die Evolution sagt ja.
them, and then we try out the robot with those knob settings, and then we measure how far the robot gets with it. And we allow the settings to prolong their life if it works well.
Die Individuen weiterverfolgt werden, die den Roboter.
So those collections of settings that work well, we retain, and we progress into the future, and the ones that don't work so well, we throw away. And it's collections of very large very large numbers of collections.
Dann optimiert es nach Geschwindigkeit, und wenn ich die.
And we can optimize for speed, or we can limit the amount of motor power.
Also nicht Motorkommando, aber quasi Motorspannung auf den Bus geben. Ja, und wenn das aufgebraucht ist, dann ist halt vorbei.
It can be controlled it can be limited either by speed, or it can be optimized for energy consumption, where you look at how much voltage and power is being put into the motors.
So I put this mirror. There's even more coming.
Oh nee. Ah ja.
So
Mal Versuch. Da ist es.
no, there it is.
Das ist jetzt
This is
ein langsames Laufen.
a slow walking. I
Und hier sieht man jetzt quasi
turn the camera a bit, and now you see on the border there are few of the commandos for the joints, and it's going up and down and wiggling around. It's not trivial, and you do not understand right now from seeing this why it's going there. The robot just needs to set his leg there and there. You might think trivially, but I tried this in the beginning But after a while, I realized, no, it's not that simple. So I opened the box of Pandora and we got to this. You don't need a regulator for the walking. You also need a regulator for standing still and finding the balance. If you don't have this, if you just turn it off, it will fall over. So I put this down. So now it's standing. And this is another regulator, which is a bit faster. There's a difference in the signals going to the motors, which in general, this model of the robot is a bit more difficult. It has more details. The motors are being modeled better, in better resolutions. There are more boxes with which represent the mass on that points. So this is one of the first models I built, the first virtual roboter, and I try to let them work. And I began with this here. It's called by Paul very lovely the walking hot dog. It's a bit more thick. It hasn't have that much of elements, and so therefore the computer can put there more signals, and it's walking Hannah, calculating it faster. We already know that Hannah from its design can't run really fast, but normal walking should be possible. So which direction do you want to see? Forward, on the left? Okay, so on the left, left should be possible. One moment, please.
Gucken, ob ich es richtig ausgewählt habe.
So see if I tried it right. Yes.
Bisschen windschief.
It's a little bit not upright. Now from the back. Oops. Laughter.
Man wundert sich jetzt so, ja, das tut es.
You might wonder, it might be hurting on the knees, but there are no sensors, so the simulated robot does not feel pain. And there are different styles, minimal differences. All these examples here are showing one after another, and if you show for a time lapse, then you see that there's a flight phase.
Sorry. Ich konnte nicht widerstehen.
I couldn't resist.
So. Ja, das ist ja irgendwie zumachen.
Now I can close this.
Und zu guter Letzt kann man
for the end,
den Renner nun zeigen.
I can show you again the running one. Where is it?
Fast, das sieht gut aus, 55.
So.
Ja, also da sind mit diesem einfachen
so you see there is a pretty simple regulator, and even with this there are very dynamic movements possible, and therefore it's a morphological problem. And you might help us to let our robots run this fast. So what's standing there? There's 2.7 meters per second. It's not very large. One of these grids is 50 centimeters.
Danke.
Is it called Hannah because it's walking forward and backward? Thank you.
Genau.
Willst du? Oder?
Do you want to take over? So yeah, now there's the question, how do you get from simulation to the real world, to the hardware? So I can spoil you. You can't bring the simulator to the same results as reality because you have finite resources and you want to have the software to run on your personal computer or your favorite cluster. Even there you see that you can put a lot of effort in and still you could simulate each joint and each nut, but you can't bring it to perfect results because the regulator will be right for the exact structure you designed there in the simulator, but not to the real world. But you tell the simulator that the robot has 4 legs, and we would like to do this, but we can't now. We would like to close the gap between reality and simulator and simulate the robot better. But you have 2 options. You can perfectize your robot, or you can just take a more simple example and put in a bit more randomness, so you have an ensemble of robots. You might, for instance, use different lengths of the legs or different mass and a bit more strong motors or less strong motors. Try to modify each parameter a little bit so that the real hardware is inside the cloud of simulated hardware, so that the algorithm which is trained to this cloud is also capable of controlling the robot. This is currently what we are doing currently now. So we try to use a simple measurement like with your ruler and put this into the simulations. We don't have very precise measurement devices. With this procedure, we try to optimize a robot.
Lass mich Matthias mal kurz noch ein bisschen an dem Roboter da rumfummeln, um den Teil, auf den die meisten warten, vorzubereiten. Sie sollen ja schalten.
I'll switch on the Christmas tree.
Wir haben 2 Jahre jetzt da schon dran rumgebastelt.
We've built on this for 2 years. You can see it's not finished. There's still enough to do.
Von der Hardware an, also wir müssen sie ein wenig robuster machen, weil
we need to make the hardware more robust. Sometimes you tip against it or it tips over. Or there are things that one could do. The strength of the motors is not very strong. We probably need better motors. We have to work on the belts because they wear out, and making them tighter is hard. And weight, adding weight is very hard, given that we've built such an inexpensive machine. The electronics, we are making the circuit board more general, so that it's not only usable for HANA, for other things. So Paul is writing firmware and drivers. And then we want to build a stronger version that we will call sensory motor cargo. And when we want to carry bigger weights, our 12-volt motors will not do. We want to know where the feet are, so we want to put sensors into the feet, so that we notice when it hits the ground. We want accelerometers on the circuit board.
Schwerkraftreferenz, die ja immer auf dem Beschleunigungssensor angezeigt wird, kriegt man.
So we want the gravity normal.
Sensor drauf, dann hat man allein schon den Torso eine bessere Abdeckung als bei einen jetzt. Und man kriegt quasi noch von den.
So we want the accelerometer on the board so that we know where the ground is.
Da reingehen, der sucht sich dann aus den entsprechenden Informationen das, was er braucht, raus.
And the model will take what it needs from those inputs So you can simply give it a bunch of sensor data, and then I look at the output at the matrix, what is actually being used. And then I look at the matrix, and it says 0 in one column, and then I know this is a broken one.
So, weil ja, wie gesagt, es gibt noch jede Menge zu tun. Falls jemand Interesse hat, sich zu beteiligen, freuen wir uns immer über Kontaktaufnahme.
We appreciate your contacts, your contact requests.
Hannah zum Laufen zu bringen. Genau. Matthias hat vorhin schon wieder gesagt, wir lassen uns nicht nochmal blicken, wenn sie nicht selber läuft. Das ist jetzt hier mit dem
Team dann auch Matthias said, we will not come again if it doesn't walk by itself. And we wanted.
Sie wird jetzt nicht über die Bühne rennen,
we want her to move by herself.
Was so der aktuelle Stand ist und,
so we want to show you where we currently are with this.
Also wir sehen jetzt hier nochmal.
At the moment, you can see the sensor input. White is the position. Light blue is the motor signal. Nothing is being controlled. Orange is the velocity. Now I'm moving the other leg, and you can see it up there. And now, if we move it to a certain position, that's a position control. If I work against the position, then you see a yellow bar going up and down. That shows the effort expended, not the power, the work being performed. I've seen something just now. Let me switch this off. Let's not switch off the whole room. Someone else switch it. So the spike is when you switch it on. That needs improving. Something that needs to be worked on. So now let's put it into standing position. Okay. Something is tilted.
Kleinen Kinderkrankheiten noch und man sieht, es ist alles noch sehr wackelig.
It's in its infancy and
Es ist jetzt ein ganz einfacher Halteregel, ohne Intelligenz daherkommt. Sowas kann man dann doch in 5 Minuten.
It is not very stable.
Mit dem entsprechenden Lehrbuch an der Hand. Und ich schalte jetzt mal kurz um nur mal unseren ersten Versuch euch zu zeigen.
Now I'll switch to our first experiment.
Was ist denn da oben für eine Zahl? 0,12. Ich darf es nicht übertreiben, weil ansonsten habe ich 2 Tage Arbeit, die Hardware zu reparieren.
I can't overdo it, otherwise I'll have 2 days to repair the hardware.
4 schalten.
Let's switch it to 4.
So. Also das ist jetzt ganz naiv, einfach ohne weitere Anpassung der Regler, den wir eingangs gesehen haben, auf den Roboter.
This is the naive control. So at least it's holding and it doesn't walk.
Dann werden diese Reflexe ausgelöst. Ja?
So if I do this, then these reflexes are caused. And I don't know what's now happening, but
ich muss es ein bisschen halten, ne? Sonst fällt es.
I need to hold it because otherwise it's falling down. Okay, something has been connected. It's been a belt. No one should have heard it by now, but I need to tell it because I was told that things which aren't heard on the screen I need to tell. So maybe it means that I need to recalibrate a sensor. I can't go further because my notebook would fall down to the floor. Felix, please press one of these buttons. Yes, thank you.
Genau, und
right.
hier endet dann auch
So this might be the end
Demo-Teil.
of our demonstration.
Ist hier noch was zu sehen?
Is there something more to show? Yes, there's something more. We thought always that we need to be fast and planned a quarter of an hour for questions, and we see that we are perfectly in time. So now it's on you. If you have questions, please let us know. Go to the micro.
Es hat sich tatsächlich gelohnt, vorne zu sitzen. Ein beeindruckendes Gerät, muss ich sagen. Also, wir haben 2 Mikrofone hier im Saal. Eins ist die Nummer 1 auf der...
We have 2 microphones in the room.
Eins ist die Nummer 2 hier im Mittelgang. Stellt euch da bitte an, um die Fragen dann zu
stellen. Please go to the microphones to ask your questions. Microphone 1.
Das ist ein sehr schönes Projekt.
A very nice project. Do you have links on your page to the learning algorithm and to the details of the learning?
Not so far, because the algorithms are part of my research work, and Ash is on my top. My professor is sitting there, but it's soon to be released. But I need to write it down in a sorted way, but we can spoil a little bit here. That's sad. And we are working on it. We are saying it's open source, but we are so much in the work that we forget about that.
Mikrofon 2, bitte.
I understand it, so thank you.
Meine Frage ist, wie stellt ihr euch die Zusammenarbeit vor?
My question is,
die da mitmachen wollen?
how do you think about collaboration?
Mit der fehlenden Veröffentlichung.
Since you've not published it, is there a contact information?
Yeah. Yes, we have a page. It's in the Fahrplan. It will be filled over time, and there is a contact. We will contact you as fast as possible by email or something similar.
Mikrofon 1, bitte.
Mit welcher Software habt ihr das Simulieren gemacht?
What software have you used for the simulation and to learn it? How did you make them talk to each other?
So the simulator itself is written in C++. It is not a standard simulator, but you could, for instance, use a project which is called Gazebo, which is an open source simulator. You can use this. It is an open source simulator. It is able to do a lot of stuff like friction and similar aspects. The software itself we showed here is written in C++. It's not standard. It's in the simulation we just use the standard C++ library of the current C++ version, and due to the current nets, it's not that we are using deep learning or TensorFlow. It's really a one layer neural net. Is so-called shadow learning.
Mikrofon 2, bitte.
Ja, habt ihr mal euch Gedanken gemacht,
Hardware
in diese Loop-mäßig in die Simulation einzubinden oder Messergebnisse wieder zurückzuspeisen, um die Modelle zu verbessern?
To change the hardware as a part of the development cycle and the feedback of the optimization.
That would be nice. So the evolution model is right now able to modify the parameters of the robot, and you could think about coordinate the measurements and feed it into the algorithm. But if you use, for instance, OpenSCAD to parameterize your models, then maybe the simulator could say you need to make the length of this leg 40 centimeters, and you could realize it using the laser cutter. But this is a lot of work, and yeah, it's a big field.
That was almost my question.
Die nächste Frage wäre, wollt ihr wirklich, ich sag mal, ein echtes neuronales Netz aufsetzen,
Do you really want a neural net to learn this? At the moment, you're not using a neural net, you're using a genetic algorithm.
Ein richtiges neuronales Netz.
You want a real neural network to learn your sensor model.
Ah, okay.
Wir haben schon teilweise so Testläufe, wo wir...
We already did some test runs where we used the motor, we saved all the data from the motors and then have a nice model. I currently do this with a self-made friction model and a motor model. In principle, the things are very clear, but to close the simulation gap, it's not enough to use my own model and fit it to the data. But you also could use, in that case, you could use a three-layer net to fit the data to the model. But I think this is going in the wrong direction. You should more train the net to a more general approach so that you can use 8-bit sensors or 16-bit sensors. So being it more general and make the net more robust, give the net one layer more to go more to the and going more to the general case where you don't depend on the number of sensors. So make it more general, the controller and the sensors.
Die Welt ist groß.
The world is big.
Eine Frage aus dem Internet.
Question from the internet.
Ja, das Internet fragt, ob ihr ein Robot Operating System unterstützen wollt.
Would you support a robot operating system?
Ich höre mich, jetzt höre ich mich wieder.
Yeah. As a matter of fact, a colleague of mine is working with two of these motors and he built a camera control for this, a camera gimbal. And we were asked if we could or should support ROS with this. And I think we are dealing with the how to deal with the biggest problems, and currently we don't support such projects right now.
Okay, Mikrofon 2, dicht ans Mikro gehen.
Ich wollte fragen, ob es bezüglich Leichtbau schon konkretere Vorstellungen gibt.
Do you have special ideas on building it with lighter materials?
Und denke, dass man ja auch budgettechnisch gerade bei der Materialwahl etwas eingeschränkt. Was ist da die Strategie?
What is your strategy for material choice, especially with respect to cost?
I think we don't have a strategy on that. I think we have these design principles we have, and if you have something which is just available in one place in the world, it's not what we want to do. For instance, if you're using the carbon rods here, and you might think it's expensive, but if you see that you can handle this, just cut one piece of the rod and then you can use it, I think this is okay. The wood is also very lightweight and stable, but on the other hand, it might twist, and so it's not made for eternity. But if you have ideas to bring us further and the ideas won't ruin the planet, please let me know. I'm really hungry for new materials to use. I would more like to put in one more kilo of batteries in there. And 3D printing of screws is a bit more expensive, but maybe in 2 or 3 years. Joking.
Es kann sein, dass ich das jetzt verpasst habe, weil mich Nick mit Tequila abgefüllt hat, aber habt ihr ich denke da an Propriozeption von diesen Gliedmaßen.
So I'm thinking of proprioception of these limbs. Do you have modules or limbs that are directly connected to the axis of the motor? You don't want to have it connected straight to the leg or to the joint. or are you going to do you have it all in one place, or do you change it?
So the most direct approach right now is that everything is going over the I2C bus to the controller. But you could, for instance, put the controller directly to the leg, and you could put there more sensors, 3 or 4, before it gets critical. You also could put there a motor just to get the sensory data. The circuit board is just put on the motor. What we first did was open the servo motors, remove the circuits, put our new in. Maybe we could use smaller ones and put in some 3D, some measurement for movement and strength.
If you put the same sensor onto the driven axis, then you can measure the belt.
Okay, I was completely wrong. It's already in the doing. The magnet decoder is in the cupboard, and we wanted to put it on the other axis so that we have the tension between the both ends of the legs, and see if there is force on the both of the joints, between the both of the joints.
Brauchte die Motorachse überhaupt? Also er wollte ja nur die angetriebene Achse haben.
Das würde ich schon gern haben.
Do you need the motor?
Do you need the motor axis, or are you only interested in the driven axis?
So yes, we could try it. It would be a more round image of it, a more round model, but not so far.
Thanks for the presentation.
Man sieht ja, dass die Hardware recht fragil ist.
I can see that the hardware is fragile, and if you even want cheaper materials, then it's not going to get more stable.
In der Simulation als Ziel zu setzen, dass das möglichst gelenkschonend ist. Oder
so would it make sense to set it as one of the parameters of the simulation to preserve the joints and put less stress on the joints?
I have big hopes on that, that we could prevent the impacts, but you see a lot of this in the simulations and you draw your conclusions from tests. I've already come to the idea that it's very difficult in the real world to draw conclusions from simulations. Everything which is you're getting from the simulations, if one joint is being hit the ground or something, I didn't want to do it so far. But if you would use this and use some feedback, it would preserve the robot. Currently, we try to make the hardware so robust that it can fall over a few times of the day, but later on it should be more robust.
Another question from the internet.
Ja, und zwar die Frage, ob es keinen zentralen Task für die
Is there
Software
not a central task for the software to control the legs?
bezogen ist das hier, glaube ich, gemeint. Also ob jedes Bein für sich alleine lernen muss,
Does each leg learn by itself
Richtung läuft, oder ob das gemeinsam gelernt wird.
how to learn in a certain direction, or is it learned jointly?
So it's in general learned all together. You need to imagine that the one single task, so it's not a multi-processing team, it's not a multi-process system, it's just one task. And 100 times per second the net is calculated and in a new sensor data read in. So the net is one task. To switch from one behavior to another, it would mean to switch from one net to the other. You also could do more complex nets. You speak from coexistence actuators. But you could, in theory, put the standing, the starting walking, start and the walking in one net to be controlled by one signal from the outside, but in general, it's one task.
Okay. Nicht weiter nach hinten, Matthias.
Nicht weiter, nee. Dann
So,
falle ich
genau.
so wie
die Bühne endet tatsächlich
wie Atlas, falle ich dann runter.
Letzte ganz schnelle Frage vom Mikrofon 2.
Last question.
Toller Vortrag. Eine Frage, kann man die Servoelektronik irgendwo kaufen?
Is it possible to buy the servo electronics?
Ist das in Planung?
Dazu muss man sagen,
Not so far. But we have to say that we put a lot of time and effort into this to finalize the firmware and the drivers. So we want to bring this to the public, to the world. And this is one of the most important steps which is happening in 2019 and 2020. And so far that we really can to say to you, please take this, try it out, make something out of it. But it will be we are not so far now, but in the early spring it will start. You can have this. So if there's someone interested here in making nice plans and nice layouts, please send them to us.
Thank you. That was the presentation. Now, where do people find you?
Wir haben eine Assembly in der Halle 2.
We have an assembly to ourselves. It's Xhain, and you can come and join us. And the other thing is you can come to our hackspace. Now give our speakers a hand. Thank you very much. So this was the translation.